Lecture 8, Static Equilibrium, Couples, and Force Transforms. This lecture is also the last one we're going to be going through a chapter from Survey, so from the first year physics book, and this is going to be the last one where we're reviewing first year physics as well. So after this, we're going to be moving on to some new material. This represents a couple of changes in the lecture. So the lectures are going to be covering less material per lecture. So that's a plus. But on the other hand, the material is going to be newer for everybody involved. So there's a bit higher of a learning curve there. The material we've covered so far is the foundation of all of that. So the better you know this stuff, the easier the newer stuff is going to be. Statics. If nothing's moving, then nothing's accelerating, either linearly or angularly. And so you can say that the net force and net torque are both equal to 0. In 2 dimensions, this gives 2 force equations and 1 torque equation, 3 equations total, which allow you to solve for the 3 unknowns. In 3D statics, it would give 3 force equations and 3 torque equations, because there's 3 possible dimensions for rotating about in 3D. So 6 equations total. We'll see some of that in a few of the problems that we're doing this year. For now, the first year review continues with net force in the X, net force in the Y, and net torque about any point that you choose, 0. The torque is for rotation in the XY plane for these 2D problems, and therefore it's technically the Z torque. So the first of a few problems we're going to do on statics today, find the tension in the shorter wire in terms of mg. So this would be the shorter wire here. In statics, you are given that nothing is moving and so nothing is accelerating. Therefore, you can apply your static equilibrium equations and solve for some unknowns. Give that a shot. So as you can see, let the tensions in the long and short cables be TL and TS. So maybe long and short, that's what I called them. You may have called them something else. The net force on the mass in the X and Y directions are both 0. In the X direction, this gives us a relation between the 2 tensions. And in the Y direction, it gives us a relation between the 2 and gravity. So from solving this first equation, we can sub that into the second one and solve for what the tension in the shorter cable should be in terms of gravity. Since we wanted to solve for the tension in the shorter cable by the problem, it didn't really ask us about the one in the longer cable. It makes sense to isolate for the longer cable in the first equation, then sub that in to the second equation, so that the first variable we're ultimately going to get an answer for is the shorter cable. Exam question from 1D03, number 2, Planck mass. If the mass of the plank is m, find the mass of the block, given that this is in static equilibrium. So the mass of the plank means there's a weight of the plank right here in the middle of it. So how far is this from this piece? It's 1/6 of the length away. Okay, by setting the pivot point as this triangle here, we can ignore what force it's applying on the plank, and then just say, okay, well, the torque produced about this pivot point from the block's weight is equal to the force produced about the pivot point from the plank's weight. But since the block is L/3 away and the plank's center of mass is only L/6 away, half as far away, that must mean the plank's weight has to be twice as much to counteract the block's weight. So we've got that the mass of the block is half the mass of the plank. Question 3, the bat saw. A solid wood baseball bat, so uniform density, is balanced in a horizontal position to locate its center of mass. If the bat is sawn into 2 pieces through its center of mass, which piece will be heavier? Okay, so center of mass is the weighted average of position, where the weight for the weighted average is the density, as you know. For the shorter side to have the same torque as the right side about this pivot point, even though its center of mass is closer, then this must have a larger weight than this piece. Therefore, the mass of the left piece has to be larger than the mass of the right piece. Because the left piece's center of mass is closer than the right piece's is, the left mass must be bigger. Cylinder on a ramp. A cylinder is held on a ramp in an inertial frame of reference by a rope that places a force F at the top of it as below. So this rope is wrapped around this cylinder, maybe it's a spool, and the rope places a force like that. Is it possible for the cylinder to be in equilibrium if the friction force is actually directed down the ramp? Well, no. Consider the torque about the center point. Then you can see, well, to balance off this force, we need a force on the bottom going the same direction as that one for there to be no net torque about the center point. That's a good point to choose because only the weight and the normal force contribute no torque there. The weight, because it's got no distance from the center point, it's applied through the center of mass, and the normal force, because its distance away is parallel to its direction. So the sine of the angle between this vector and the normal force would be 0. Another good point would be at the top. Now we eliminate the force, but you can see the torque due to gravity would tend to make it rotate this way, whereas the force due to the torque due to this friction force has to counteract that, and so friction must be up the ramp. Next topic is couples and force transforms. This is the first new thing that we're going to be doing besides dealing with problems that we couldn't have solved before in first year about the same kind of physics. This is a new physics concept, a couple. A couple is a pair of equal magnitude, opposite direction forces on an object whose lines of application are separated by a distance L. So here's force 1, here's force 2. They're the same magnitude, but they're pointing in opposite directions and they're applied at different points along this object. To help reinforce what these do, why don't you give these a shot even though the answers are on the screen. See if you can calculate the net torque that this couple of forces produces about the left end of the bar. If you work that out, you'll find, okay, well, it's L times that F. It produces a torque in the clockwise direction given by L times F. So if we define out of the page as positive, then clockwise direction would be a negative torque, so it's negative LF. What about the torque about the right end? Well, this time we've got L and this F producing again a torque in the clockwise direction, so negative LF once again. What about the middle? Let's pick the middle of this and see what kind of torque these two forces make there. Now we've got half LF and half LF. It's the same. We have LF in the clockwise direction for all three cases. It turns out it doesn't matter where we calculate the torque produced by these forces. A couple of forces produces the same torque about every point in the bar. Before, we had to be concerned with where we picked, which point we picked to calculate the torque about, but for a couple, they produce the same torque everywhere. That's interesting. So if we can write forces that are applied at arbitrary locations as forces at the center of mass, which produce no torque about the center of mass, and couples, which you'll notice produce no net force, but just produce a torque, and it's the same torque about every point, and therefore about the center of mass, we'll be able to analyze problems easier. So ideally what we want is to find a way to turn a force into a couple and a force at the center of mass. Well, here's the construction to do that. Imagine adding two equal and opposite forces at the same spot and at the center of mass. These two, the bottom two in this picture, produce no net force on the object and no net torque on the object. So adding these two has changed nothing. It's changed nothing about the external motion of the object. If they're really applied at different points, like on different sides of the object, then it would create a compressive force in the object, but they're just drawn there for the picture. Imagine that you really would apply them at exactly the same point. Okay, now notice that this force and this force together are a couple. So if you've got a force applied a distance d away from the center of mass, it's the same as if that force were applied at the center of mass and a couple of forces given by that force times d. Question: a rod of length L and mass m is initially at the origin and oriented vertically. When it experiences a force F equals F I hat applied at d j hat from its center of mass, find the angular and linear acceleration of this rod. Force is equivalent to one through the center of mass and a couple Fd, so the force here pointing in the negative z direction. So the linear acceleration should be force over mass, and the angular acceleration should be the torque over the moment of inertia, r cross f over I center of mass. And you can carry out this cross product, or you can just say, well, the couple is Fd, and it points in the negative z direction. Why? Because we've got the force is displaced up and points to the right. So this would make a torque in the clockwise direction as before. And so the angular acceleration is just negative Fd over the moment of inertia. And that's it. So this was a bit of a shorter lecture, and that's to make room for the next couple of topics, which are pretty complicated and going to be largely new material with a lot of tricky problems on there. So to make room for what's coming next, we're gonna just end here and treat this as a bit of an easier topic.